Hello friends, this is lecture 7 of a series where we go through the book on quantum mechanics by Steven Weinberg. This is chapter 2 on the states of a particle in a central potential. As explained in the first lecture, we will be reading the book in the sequence chapter 3, then 2, followed by 1, and continue from there according to the regular order of the book. In chapter 3, we have established the formalism of quantum mechanics, the states of a quantum system, and what could be measured about it, the observables, and how they evolve in time. In this chapter, we begin the study of an important class of problems in quantum mechanics. These are the situations when a particle moves under the influence of a central potential. The Hamiltonian for this is given by. What we meant by a central potential is that V is only dependent on the distance of the particle from the center of the potential, taken to be the origin. Quantization of this Hamiltonian just means replacing both the position and momentum by the corresponding operators that satisfy the canonical commutation relations. Our main concern will be to solve this eigenvector equation. This is often referred to as the time-independent Schrodinger's equation. We shall solve for the energy eigenstates, and of course, the associated energies will reveal themselves in the process. But first, it will be good to know if these states are also eigenstates of any observables other than energy. These are observables that must commute with h. The additional constraints provided might simplify the solution to the energy eigenvector equation. This will be clear in a minute when we get to the specifics. The rotational symmetry of H suggests that the generators of rotations might just be such observables. As explained in lecture 5, the generators of any symmetry of H must necessarily commute with it. The generators of rotations will turn out to be the angular momentum operator, as we shall see. H is obviously invariant under rotations because it is a function of only the magnitudes of vectors. Here we are assuming that the position and momentum operators transform like regular 3D vectors under rotations. Such operators are called vector operators, which will be collectively denoted by V. Let me remind you how a 3D vector rotates about an arbitrary axis using the position vector as an example. X rotates into x prime through an angle of delta phi. It is sufficient now to just look at infinitesimal rotations. Let's look at the change in position. Since this change is infinitesimal, its direction is along the tangent vector, denoted by the yellow arrow. This is in the same direction as the cross product of the vector n and x. Therefore, the magnitude of delta x is given by that of the blue arc. This means multiplying n cross x by the rotation angle delta phi will give us delta x. To make things more compact, one could combine the rotation angle and axis and define the vector of infinitesimal rotation. And we have the transformation of x to x prime under an infinitesimal rotation. This will be the prototype of how vectors transform under rotation. If x is taken to be the position operator, then the rotation must be affected by an unitary transformation, like so. Just like an observable would, transforming under a symmetry in Heisenberg's picture. We have explained this in lecture 4. Then we could use identity 1, derived in lecture 3, to evaluate this if we take G to be position and C to be the rotation generators. Recall that the adjoint action of C on G is just a commutator between them. For an infinitesimal rotation, the right-hand side of identity 1 would approach the following, where c is kept only to the first order. Applying this to the rotation of x, we have this change of x due to unitary transformation must be equal to that prescribed by the rotation of a vector. And we are led to this commutation relation between the rotation generator L and the position operator x. This equation will help us figure out what L is. Let's write this in components form to factor out delta phi. Once again, we have used the Einstein's convention where repeated indices are summed over. I hope you are familiar with this identity of the cross product. If not, it's quite easy to verify. How should L be defined in order to satisfy this equation, assuming that it is a function of x and p? It is easy to guess that this is a suitable candidate. Let's check. We can use the product rule of commutators introduced in lecture 1 and bring the commutator of xj straight to pk, omitting xl since different components of x commute with each other. Using the canonical commutation relation for this, we have bringing the index j to the front, we get the correct result for the right-hand side of the equation above. Similarly, let's look at the rotation of the momentum operator by replacing x in the blue box at the top with p. We can use the expression for L in the blue box, which is just shown to generate the correct rotation for position. Let's see if this will work for momentum. So L rotates the momentum correctly as well. Therefore, we have the correct rotation generator. Let's rearrange the rotation condition in the yellow box a little. This equation defines how any vector operator transforms under rotations. In a minute, we will show that L itself is also a vector operator. The change due to an infinitesimal rotation of a vector operator is generated from the commutators in this way. This is equal to the form required by how vectors are rotated, as we have shown earlier. Finite rotations can be built by combining infinitesimal rotations. And the transformed vector is just the original vector v multiplied by a rotation matrix. An example would be a rotation on the xy plane. We shall have more to say about the quantum theory of rotations in Chapter 4. Let's take a closer look at the generators of rotations. What observable is this? Notice that because of the Levi-Civita symbol, the indices L and K are never equal, therefore the corresponding position and momentum operators always commute. This means there is no ambiguity in operator ordering in this definition. We could express this in the familiar form of the cross product. So we have shown that the generators of rotations is the angular momentum operator, as promised. More specifically, this is the orbital angular momentum, to distinguish it from the internal angular momentum, which is the spin of the particle. This momentum gets its name from the orbital motion of an electron around a nucleus. Let's look at the units of L. It is length times momentum. From de Broglie's formula, momentum has the units of h bar times the inverse of length. This means angular momentum has the units of h bar. This is a fact commonly used in quantum mechanics. For this operator to be an observable, it has to be Hermitian, but is it? Let's check. Note again that because of the Levi-Civita symbol, pk and xl always commute, therefore we could switch their order. So we have shown that L is Hermitian. We now demonstrate that the square of any vector operator is unchanged by rotation. This is clearly so for ordinary commuting vectors. We now need to show that this is also true with vector operators, being more careful with operator ordering. V-square transforms in this way, assuming that the transformation is infinitesimal. It is sufficient to prove invariance under infinitesimal rotations, since finite rotations is built out of these, and will therefore be invariant by implication. Applying delta V in the yellow box. Expanding this out, keeping delta phi to the first order. Be careful with operator ordering as we did for the last two terms. Here we can make things clearer by expanding the triple vector product in components form. In the last equality, we have simply switched the dummy indices j and k and have not altered the orderings of v. Let's bring the index j to the front in the Levi-Civita symbol and switch the order of I and k, incurring a minus sign. Notice that in the whole process, the orderings of the products of v are being preserved. No assumptions are being made about whether the different components of V commute with each other, so our result will be quite general. The last two terms therefore cancels each other. And we have proven the invariance of V square under rotations. The consequence is that the generators of rotations, L, commutes with V square. Next, we show that L itself is a vector operator, so it should rotate like one by the rule in the yellow box. Our task now is to show that this equation is true. Let's substitute the definition in the blue box. We can distribute the commutator with the product xn pm among xl and pk using the product rule of commutators. The product rule can be applied further, one level in, and we get from the canonical commutation relation. pk and pm commute with each other. If you are not familiar with the product rule of commutators, refer back to Lecture 1 in the description below. Or we could simply apply this useful result from Lecture 2, which is just another way to express the product rule. There's a similar relation involving the commutator with xi instead. This is applied to the second commutator. Consolidating these results, we have the product of two Levi-Civita symbols in the red box seems quite complicated. We need an identity to simplify it. This is given in the yellow box. Note that the index I is summed over by the Einstein's convention, while indices L, K, and Mn are free. It is not difficult to see why this identity is true if we do it systematically, step by step. Let's first look at epsilon ILK. Choose any two values for L and K. They must be of different values, otherwise epsilon will be 0. For example, L equals 2, K equals 3. This automatically implies I equals 1. This has the following implications for the second epsilon. Since the blue index, which is summed over, must be equal to 1, we are left with these two possibilities. Compare the first possibility to the epsilon in a green circle. This means L equals N and K equals M. Since the value of epsilon 1, 2, 3 is equal to 1, this corresponds to the first product of Kroneker's deltas on the right-hand side of the equation above. The second delta product is equal to 0 and doesn't contribute, as the index pair of each of the delta symbol are of different values. Therefore, for the first possibility, the identity at the top is correct. For the second possibility, the M and N are simply switched, corresponding to the value of the second delta product, since epsilon 1, 3, 2 is equal to minus 1. Now the first delta product is 0. So the identity is also true for this case. Thus we have proved the identity for the contraction of two Levi-Civita symbols. Here's a good way to remember this. The first index of the two epsilons are summed over. The second indices being equal leads to one Kroneker's delta. The third pair being equal leads to another delta. The second epsilon must be antisymmetric with respect to its second and third indices, N and M. This leads to the second pair of deltas with a minus sign, with their second indices switched, with respect to the first pair of deltas. Let's get back to our proof of L being a vector operator. We are trying to simplify the expression in the green box where we encounter the epsilon product. Looking at the first term in the brackets, we apply the Kroneker's delta to the epsilon product. Moving the index k in the second epsilon to the front, a minus sign is incurred. The same is done for the first epsilon without a minus sign, since k is moved past two indices. Finally, we switch the indices I and L in the first epsilon, absorbing the minus sign. In this form, it is easy to apply the identity in the yellow box. The first pair of deltas fix the indices of x and p to j and I. The second pair of deltas contracts x and p, leaving one delta carrying both the indices I and j. Similarly, let's apply the identity in the yellow box to the second term within the brackets. Again, the delta in this term contracts the indices L and M between the two epsilons. Rearranging the indices to a convenient configuration, we can again apply the yellow box. These two delta products, when applied to xn and pk in the green box, give the following result. Notice that the second and the last term cancels each other. Now we apply the identity in the yellow box in reverse, meaning the antisymmetric product of x and p is expressed as the contractions of xl and pk with two pairs of delta products. L and k are dummy indices that are summed over. Notice that the entire term above the yellow braces is antisymmetric with respect to I and j, consistent with the left-hand side of this equation. These delta products can be expressed as the product of two epsilons by the identity in the yellow box. And we recognize that the term in the blue box is actually the component of angular momentum Ln. Thus both sides of the equation at the top are equal. Therefore L is a vector operator and transforms correctly under rotations.